So this is our last lecture in Unit 2, Energy and Momentum, and this is on perfectly elastic collisions. Your textbook refers to this as head-on elastic collisions. It's section 5.4 in the textbook, and I'll go through this. It's similar to, we've analyzed the collisions previously, and we saw that collisions are usually somewhere between, they have some elasticity to them and they have some inelasticity to them. In a perfectly elastic collision, the kinetic energy is conserved throughout the collision, before, during, and after. In reality, we do not have perfectly elastic collisions, but we will have a lot of collisions where there is a very small loss of kinetic energy, and we can use the concept of a perfectly elastic collision to help us solve for unknowns in a problem of that type and get very accurate answers. So since both kinetic energy and momentum are conserved in perfectly elastic collisions, an analysis of this type of collision yields two very useful equations. Now, I'm not going to go through these. They're covered in your textbook on how you can derive these on page 240 and page 241. So if you want to look at that, please review your textbook. But these collisions, or perfectly elastic collisions, can be solved using two simplified equations that come from the conservation of momentum equation. And those are VAF is equal to the difference between the masses divided by the sum of the masses times VAI. And for VBF, it's equal to 2 times the mass of the moving object divided by the sum of the masses of the objects times the initial velocity of the first object. Now, for these equations, and if you read your textbook, you'll understand this as well. Object A is moving, object B is stationary. So that's very important. Without that, these equations come a bit more complicated. But in reality, we can always set our equations in such a way that our object B is stationary relative to object A. And I'll show you how to do that in the future, a little bit further on in this lecture. But just keep that in mind that I think it even says it on your formula sheet. There's this note that these equations assume object A is moving and object B is stationary. So this problem says, suppose you have two objects. Object A has a mass of 0.26 kilograms. It's traveling at 1.3 meters per second east. It collides head-on with a stationary object B with a mass of 0.15 kilograms. It says the collision is perfectly elastic. So because it says it's elastic, we can assume it's elastic. In other cases, with a collision problem, if it doesn't say it's elastic or inelastic, then you can't assume it's either. You'll have to do a different type of analysis before. And we're asked to determine the final velocity of both objects and express our answer to two decimal places, which is a little bit different than expressing our answer with two significant digits. So I'll get into that a bit later as well. So let's try this problem out. So in this problem, as with any perfectly elastic collision problem, we have the two equations for the final velocity of object A and the final velocity of object B. Now, the first thing we do when we look at a problem like this is we're going to check to see if object B is in fact stationary. And if we look back at the question, it says that it collides head-on with a stationary object B. So we don't have to do anything else to these equations. So we can start just by substituting in. So I will copy out VAF. It's MA minus MB, so that's going to be the mass of A, which is 0.26, minus the mass of B, which is 0.15, over the sum of the two objects, times the initial velocity of A, which is 1.3. And we might as well fill in VBF here. So it's 2 times MA, which is 0.26, over 0.26 plus 0.15 times 1.3. So for each of these, let's see, we have 0.26 minus 0.15, which is 0.11, divided by 0.26 plus 0.25, which is this value here, this ratio, times that by 1.3, and we end up with a VAF of 0.3488. Our VBF is 2 times 0.26 divided by 0.26 plus 0.15. So this ratio times 1.3, we have 1.6488. Now in the question it says express your answer to 2 decimal places. So that's not the same as doing significant digits. If we were looking at significant digits, we would represent only 2 significant digits, which in this case would be 3.5 meters per second, and this is to the east. And over on this side, it would be 1.6 meters per second to the east. However, for this problem, it does say express your answer to 2 decimal places. So that means that we're recording to the hundredths digit. So this would be rounded up to 5. A little bit of a different way of representing our answer. You probably won't see that too often in this course, but I just wanted to point that out. The difference between representing an answer to 2 decimal places versus 2 significant digits. 2 significant digits here would be 0.35, and here would be 1.6. Okay, let's look at our next problem. So this is a more complicated problem. So it says, suppose object B in the previous problem was not stationary, but was initially traveling at 1.0 meters per second west. So what would be the final velocities of both objects? So we could still use our perfectly elastic collision equations, but we need to do something first. We need to set our VBI to 0. And to do that, we need to kind of add our velocity, add the opposite velocity to it. So if it's traveling 1.0 meters west, we're going to add 1.0 meters per second east to that to make it 0. But we have to add that again to our VAI, because that would relatively VAI would be traveling faster. I know it's kind of shown there, and it says make VBI equal to 0 by adding or subtracting the opposite number. And then what you did to VBI, you have to do to VAI. And then you find VAF, and then you do the opposite operation of what you did previously. And you do the same thing for VBF. So I'm going to do that on the paper now, and I'll show you where that comes from, and I'll talk through it. So our initial situation is this. We have object A that's traveling at 1.3 meters per second to the east, and object B that's traveling 1 meter per second, or 1.0, to the west. Now, relatively, what's happening is if we add to this 1.0 meters per second east to both of these, what we end up with is a situation that looks like this. We have object A traveling at 2.3 meters per second east, and object B is stationary. If we're looking at the relative velocities here, A's velocity relative to B is 2.3 meters per second, because A is moving 1.3 towards it, B is moving 1.0 meters towards it. So what would happen is after 1 second, A would be 2.3 meters closer to B. So relatively, it's moving at 2.3 meters per second. And if we consider that, then B, we could argue, would be stationary relative to A. If we just look at the case of A moving 2.3 meters per second towards B, we can consider B as stationary. Now, what this means for our givens, our VAI is 1.3 meters per second east plus 1.0 meters per second east So our VAI is 2.3 meters per second east. And our VBI is 1.0 meters per second west plus 1.0 meters per second east, which is the same as 1.0 meters per second west minus 1.0 meters per second west, which is 0 meters per second. So going back to these equations here, and I will just rewrite them to make this easier to see. VAF is equal to MA minus MB over MA plus MB times VAI. When I substitute this in, I have 0.26 minus 0.15 over 0.26 plus 0.15. And my VAI is 2.3. So this becomes, I'll do this quickly here, 0.26 minus 0.15 divided by 0.26 plus 0.15 gives me this ratio, times that by 2.3. I end up with a 0.617. Now, what I need to do to get this back, this is 0.617 to the east, rather. To get this back to this is its velocity relative to object B. Now, to get its absolute velocity, what I need to do is I need to add back what was missing, or rather subtract. So I added 1.0 meters per second east, so here I have to subtract 1.0 meters per second to the east. And if I subtract that, I end up with a negative 0.383. And when I round to two decimal places, 0.38 meters per second, and that is going to the the west, because it was negative. So I'll quickly fit in this last part here. Let me just put the paper over here so I can use that space. I like to save as much paper as possible. So the other value to solve for is VBF. And VBF is 2MA over the sum of the masses multiplied by VAI. My VAI I'm going to use is the that alternate VAI that I used previously. So that value is 2.3 meters per second to the west. So 2 times 0.26 divided by 0.26 plus 0.15 gets me to this value here. And what I need to do with this is I need to, so I'm going to write this down as 1.268. Now I need to subtract the 1.0 meters per second east that I initially added. And that would be subtract 1. It gets me to, sorry, just a second here. I think I screwed something up. Let me just retry this. 2 times 0.26 divided by 0.26 plus 0.15 times 2.3. There we are. So 2.9. So I wrote down the wrong number here. 2.917. Subtract 1.0 meters per second east. And that gets me to 1.917 or 1.92 meters per second to the east. So this next problem here says, without doing any calculations, draw some general conclusions about perfectly elastic collisions, and they give us three situations. The first is when m1 is equal to m2, and let's look at these equations here and figure out what would happen. So I've just slid them into screen. If m1 is equal to m2, then for VAF, we would have a 0 in our numerator because MA in this case would be equal to MB. So our numerator would be 0. This would be 2 times that mass. But 0 divided by anything is 0, meaning that 0 times VAI would be 0. So VAF would be 0. This would imply that our object A, or our object 1, would stop. And then what happens over here? If we have VBF, which is 2MA over MA plus MB, and really, in this case, MA and MB are equivalent. So we would have 2MA over 2MA, which would reduce down to 2, and it would be 2 times VAI. So we would have our, it wouldn't be reduced to 2, it would be 2M divided by 2M. So we would have 1. So that means that VBF would be equal to VAI. So we would have our mass 1 hit our mass 2. Mass 1 would stop completely. Mass 2 would carry on moving at the same velocity that mass 1 was moving at initially. Another situation they asked us to look at is if M1 is much, much greater than M2. So in that case, if we had MA minus, and it was in the order of 1,000, and MB was in the order of 100 grams or even 10 grams or something, the difference between these values would be very small, and the sum of them would be very similar to MA. So in this case, the initial velocity of VAI would be similar to the final velocity, VAF. It would almost kind of plow over the other object. And in the second case here, it would be 2 times MA, which is a very large number, over what's essentially MA, because MA plus MB, when MA is very large compared to MB, could be considered similar to MA. So this would be 2 times VAI. So VBF would be moving twice as fast as the very large MA that hit it. So when mass 1 is much larger than mass 2, you can almost ignore mass 2. Mass 2 ends up moving twice as fast, and V1 or VA almost has no effect to it at all. It continues moving at the same velocity. The next situation they ask is the opposite. If M1 was much, much smaller than M2, so this M2, again, this implies that M2 is stationary. And if that was the case, looking over here at this equation, if this was a very large number, this was a very small number, the subtraction between these would be similar to negative MB. The division here would be similar to MB. So this entire term would be similar to negative 1. So our final velocity for A would be almost the opposite of its initial velocity. So it would be minus VAI. So it would hit the object and bounce back. It's almost as if it was hitting a wall, and it would have no loss of energy. VBF, the final velocity of M2, would be 2 times a very small number over a very large number. So that would be a very small number altogether, times VAI would be a very small number. So our VBF, our final velocity for 2, would be very small, almost close to 0 actually. So our situation would be that our object A, the smaller object, would hit object B, bounce back with almost the same velocity that it was traveling towards the object, and object B would be moving would almost not be moving at all. So this question then says, consider 2 carts shown below. What do you suppose happens to the total mechanical energy during an elastic collision? And I'll just read what it says on this next slide because they kind of cover it really well. It says, when 2 gliders collide, the spring bumper compresses initially and then springs back to its original shape. This occurs because some of the kinetic energy of the moving gliders is converted into elastic potential energy in the spring bumper during the compression, which is then converted back into kinetic energy during the rebound. And this kind of shows you what's happening here. So the graph shows that as the spring compresses, the elastic energy increases and the total kinetic energy of the two carts decreases. The total mechanical energy, however, stays constant. As the compression decreases, the elastic energy decreases and the total kinetic energy increases. But that total mechanical energy is still constant. So there's this moment of collision where we're losing kinetic energy and we're gaining elastic potential energy. There's a moment where we lose all of our kinetic energy and we have our maximum elastic potential energy. And that maximum potential energy is equal to the kinetic energy before the collision. And then it disperses again. So we have that conservation of mechanical energy throughout. And the last thing we'll do is we'll look at a problem here with a collision between two carts with springs. So we have a dynamics cart that has a mass of 1.8. It's moving at the velocity of 4.0 meters per second to the right. We're going to ignore friction for this problem. And then we have a dynamics cart with a mass of 2.2. It's moving 6 meters per second to the left. The carts collide in a head-on collision and are cushioned by a spring, and we're given the K value of that spring. So we're asked to determine the compression of the spring during the collision when cart B, or cart 2, is moving at 4 meters per second left. So that's kind of an interesting question. We're not talking about when it's at maximum compression. We're talking about the point where cart B collides with the other cart and slows from 6 meters per second left before the collision to 4 meters per second left. But the collision is still kind of happening. So these are the givens for this problem. We have M1 and M2, their masses, V1I and V2I. One is going to the right, one is going to the left. Our K value is listed. Our V2F is going to be 4.0 meters per second to the left. Now this isn't our final velocity in terms of after the collision is complete, but this is during the collision. Our V2 is going to slow from 6 to 4. And we want to know how fast, our unknown in this case is what is V1F when V2F is 4.0 meters per second to the left. Now, in order to do this, because we have a non-stationary object 2, we need to make object 2 stationary. So our V2I prime has to be, we're going to subtract 6.0, this is a subtraction sign, meters per second left from the 6.0 meters per second left of V2. That gets us to 0 meters per second. So now that we have a V2 of 0 meters per second, we can use our equations that we that are for elastic collisions. So we have to subtract 6.0 meters per second to the left from the initial velocity for object 1. That's the same as adding 6.0 meters per second to the right. So we have 10 meters per second to the right. Now for this question, because we're mostly to the right, I'm going to take right as positive and left as negative for the rest of this question. And we'll only report those directions at the end. And you'll notice the one way I like to do right and left is with an arrow pointing to the right or an arrow pointing to the left in brackets, square brackets. You can do any way you'd like. You can put R's and L's, but that's one way I like to do it. So now what we're trying to do is we have to find out what is our VAF when our V1F when our V2F is 4.0 meters per second. So this V1F, it's similar to, let's write out this equation here. So we have V2F equals 2MA, or 2M1. I'm going to change the M's and A's to 1 and the b's to 2, times V1I. This equation here is one of the elastic collision equations. What I'm going to do in this case, this V1F that I'm looking for here will be equal to this V1I in this equation if I substitute this intermediary V2F in for this. So 4.0 equals 2 times 1.8 over 1.8 plus 2.2 V1I, and that's going to be 4 times 1.8 plus 2.2 is 4, divided by 2 divided by 1.8 gets me to 4.444. Now, one thing I did forget is that this is negative because this is going to the left. So I'll have a negative 4.444. So I'll make this negative by multiplying by -1. Now I have to add what I've taken away, which is this -6. So I have to add that 6 to this value. So plus 6.0 meters per second. So this plus 6 gets me to a 1.56 meters per second to the right for my V1I, which is actually my V1F for this specific type of problem where I'm looking at that point in the collision where we've slowed our V2 from 6 to 4. So now I have to look at the kinetic energy involved. And in this case, I can't use my my relative velocities. I have to use my absolute velocities. My EKI for 1, sorry, my I'll call it EK1I. My EK2I has to be equal to my EK1F plus my EK2F plus the potential energy stored in the spring. And in this case here, I'll write out all of these, and I'll show you what we can remove. So we have 1/2 M1 V1I squared plus 1/2 M2 V2I squared equals 1/2 M1 V1F squared, which will be this V1F, plus 1/2 M2 V2F squared, plus 1/2 of K delta X squared. Everything has a half, so I'm just going to multiply everything by 2, get rid of those halves. And to isolate for delta X, what I'm going to have is 1 over K square root of everything to get that out of there. That gives me an M1 V1I squared minus M2 V2I squared. Sorry, that's plus that. Minus this value here, which is minus M1 V1F squared minus M2 V2F squared. So now I can substitute my values in here. My 1 over K, this is 8 times 10 to the power of 4. My M1 is 1.8. My V1, I have to use this V1 here, which is 4 squared. Then I have 2.2 times V2. Using this one, I have 6. minus 1.8. My V1F is this value, 1.56 squared. My M2 again is 2.2, and my V2F was 4.0 squared. So what I'll do, I'm going to save this in my memory so that I can reuse it. That way I can recall that at any time. And I will close this bracket at the end here. I'll divide by my k last. So I have 1.8 times 4 squared plus 2.2 times 6 squared minus 1.8 times this value squared minus 2.2 times 4 squared. Okay, so that gives me 68.44444. So that divided by 8 and divided by 10 to the power of 4 gets me to this value. And then if I find the square root of that, I end up with a delta x of, and I had two significant digits, so I'll round to two significant digits, 0.029. That is in meters. And I think in the answer we were asked to report it in centimeters. Let me just quickly look back. Determine the compression of the spring in centimeters. So quite often you'll get a question where it's asked to determine it in centimeters. So this is our answer in meters. Just next to that you can put down it is 2.9 centimeters. That is our solution. Now let's look at the next question here that says calculate the maximum compression of the spring in centimeters. So this maximum compression occurs when both of these carts are moving at the same velocity. So to solve this, we know that V1F is equal to V2F. And what we need to do is look at the conservation of momentum, M1 V1I plus M2 V2I, that equals M1 V1F plus M2 V2F. Now these two values are the same, V1F and V2F. So if we factor that out and we just call it VF, what we can end up doing here is solving for what must that final velocity be that's shared by solving this equation here. So M1 V1I plus M2 V2I, that entire thing over the sum of the masses. So let's write this out. We have VF equals 1.8 times our initial velocity, which is 4, and that's going to the right, so I'll keep that as positive, plus 2.2 times our initial velocity, which is 6, but it's negative because it's going to the left, over 1.8 plus 2.2. Now because I'm not using the elastic energy equations, I don't need to find relative velocities here. So my sum in my numerator is negative 6. Divide that by 4, I get negative 1.5 meters per second is my VF. Now that I know my VF, I know that my kinetic energy before, EKI or EK1I plus EK2I, has to equal EK1F plus EK2F plus the ES. And that is 1/2 mv1I squared plus 1/2 m2 v2I squared equals 1/2 m1 v1f squared plus 1/2 m2 v2f squared plus 1/2 of k delta x squared. This v1f and this v2f are the same, so I'm just going to call them vf. These 1/2s, I can get rid of everything here by multiplying the entire, both sides of the equation by 2. I need to solve for the delta x. So delta x equals 1 over k, and this is going to be the square root of, bracket, what's over here, which is m1 v1I squared plus m2 v2I squared, those two values, minus this value here, which is m1 vf squared minus m2 vf squared. And substituting this, let's write down all the values. Square root of 1 over 8 times 10 to the power of 4, bracket 1.8 4 squared plus 2.2 negative 6 squared minus 1.8 negative 1.5 squared plus 2.2 negative 1.5 squared. I could have simplified this by adding those together as well, but it's fine. I wrote it down like this, so I'll do that. I'm going to do everything that's in the brackets underneath the radical. So 1.8 times 4 times 4 plus 2.2 times 6 minus 1.8 times 1.5 squared plus 2.2 times 1.5 squared gets me to this value. Divide that by 8 and 10 to the power of 4. And then I find the square root. I get 0.037 or 3.7 centimeters, which is my answer. Now, we used exact values throughout. These lecture slides sometimes don't. That's why you'll see some problems. If you were given this question, your answer should be 3.7 centimeters, not the 3.5 centimeters that it says in the lecture slide.